Now, there are few things which we want to check. One is repeatability. Okay. There is linearity, meaning the response can be represented by a linear system. Stability. Okay. Stability here means we apply a perturbation, sinusoidal wave, we stop that, wait for some time, the system should come back to the original state. That is an assumption that it will come back. So, we get EAS data, we assume that these assumptions are valid, and then we analyze the data. One is called causality. Causal means we apply sinusoidal wave, we get a sinusoidal current, hopefully a sinusoidal current, we get a response, we analyze it thinking that the resulting current is due to the application of sinusoidal wave from our side. It is caused by what we do. It is not coming because of something else. In other words, it is not necessarily noise. Noise level is low. In technical term, there is another way of thinking. They would say causality here means the response cannot come before the application of the perturbation. I mean, if I apply sinusoidal voltage now, I should not get the current before this. But in practical terms, we are not going to measure before this. We are going to apply sinusoidal potential, get the response, and hope that whatever response we get is because of the application of sinusoidal potential. And one way to check is to do the experiment again and again. You should get same data. Every time it changes, something is not correct. Okay. Repeat experiments, you do an experiment, dismantle the setup, come back, redo the experiment. That if you get the same data again and again, it is repeatable. There will be some difference that gives you an idea of the noise level in data acquisition in the system put together. I want to know whether it is linear. I can apply 10 millivolts, I can apply 20 millivolts, 5 millivolts, and see whether the response is same within the noise level. If it is the same, it is within the linear limit. If 5 and 10 are more or less matching, but 10 and 20 are different, try 20 and 30, they are different, you will say up to 10 millivolts it is linear. Beyond this, I cannot neglect the nonlinear effects. All this means you will need to spend substantial amount of time to get one set of data which you trust. It takes certain number of hours to prepare the setup, maybe days depending on what you are testing. It will take at least few minutes, maybe 10 minutes, maybe 20 minutes to run one EAS. So, when I say repeat it, nobody wants to do it, but if you want trust the data, you have to do that. If I say vary the perturbation, at least you should try 2 values, preferably many. If you want to study and say this is the linear regime, you have to do it at multiple EAC 0 and then see where this is more or less the same. So, if I try, I will just make up this 10 millivolts, I get data like this. I try 10 millivolt, I will get data more or less like this. I try one more time, I will get like this. Then I say it is repeatable. And when it is repeatable, I should worry about taking 5 millivolt data, impedance looks like this, like this, like this, I will say it is in the linear regime. 20 millivolt, it looks like this, I will say it is in the nonlinear regime. If at 10 millivolt itself, I get data like this, I have to figure out how to reduce the deviations here. Then I can't say 20 millivolts also look like this, because the noise level is too much. Stability. Let us say you take the experimental setup, you do one experiment, you get data like this. At the end of it, continue with one more experiment, same parameter set. If it gives you more or less like this, you are good. If it becomes like this, that means during this experiment, system has changed to some level. So, it has not been stable. At the end of this perturbation, it has not come back to the original state. Of course, I have applied many sinusoidal sequences, but it has not come back to the original state. If it has come back to the original state within the noise level, I should get the same set of data. So, this is one way to check whether the data, experimental data, has come from a system which follows linearity, stability and causal constraint. It is also possible to validate the impedance data using a transform called Kramers-Kronig Transform. So, this is somewhat special to impedance data. Among the electrochemical techniques, this is somewhat special. Okay. You take cyclic voltammetry data, you take chronoamperometry data, and it looks good, you feel it is correct, it looks noisy, you feel something is wrong, it looks weird, you do not know whether it is good or bad. meaning cyclic voltammetry data, if you get something like this, probably it is correct. If you get something like this, I think it is wrong, I do not know. If you get something like this, I know it is noisy. So, as a cartoon, of course, this is shown to illustrate that people are relying more and more on computers and calculators, but here if somebody gives you a number, if it is possible to check it, you want to check it. Okay. So, there is a equation, it is written for impedance here. If a system is linear, causal and stable, and it gives a coupled response for various frequencies, you can relate the real part and imaginary part using this set of equations. Okay. These are purely mathematical formulations. It is applicable for impedance, it is applicable for admittance, it is applicable for optical data. In optics, you have what is called refractive index. Refractive index, normally you would have seen water has a refractive index of 1 point something. Okay. It actually has two components, one is called real and another is called imaginary. Real component tells you the deviation, when you send a light at a particular angle, it moves in another angle, etc. Imaginary component is related to how much is absorbed by the material, and that depends on the wavelength. Depending on the wavelength, the refractive index, which has a real and imaginary part, will vary. Wavelength is another way of saying frequency. Now, I can replace this with refractive index, real part and imaginary part. These equations are valid. These are not derived specifically for impedance. These are just mathematical relationship for a function which has a coupled output, two outputs. As long as it follows these constraints, I want you to note the following. Okay. Omega here is the frequency, 2 pi f. Real value of the impedance at infinite frequency. Okay. In complex plane plot, this is the first starting point. This is a high frequency data. That cannot be obtained only from imaginary data. Okay. That has to be given in addition to giving me the imaginary data on frequency. If you give that, then the remaining all the real values I can predict. If I want to predict the imaginary values, if you give me all the real values I can give. As an example, this relates real and imaginary. There are equations which relate the phase and magnitude. You can go to reference books and you can get those. And these are pure mathematical relationship, meaning when you derive these equations, you do not have to say anything about impedance. So, this is an example. This is simulated data. I have taken it 1 millihertz onwards. Because of space, I have just removed this data. Let us pretend that there is data from 5 millihertz, etc., few hertz, few hundreds of hertz, few kilohertz, and then it goes up to 100 kilohertz. And we have saved the data, real and imaginary part. It is actually minus imaginary, so these values are positive. So, this would actually look like a semicircle if I plot minus imaginary versus real. I can also plot this in Bode plot or any format. I can calculate the mod z and the phase value. Okay. Now, let us pretend that you have this data and somehow you lost these two columns. You deleted, you saved it, and then you realized you lost it. Okay. And in fact, we will worry about the z tab later, we will not look at it now, we will just say we lost the imaginary part, I want to get the real part. If this data set has come from a system which satisfies this relationship, then you can use this transformation and get the imaginary values. Now, you can't just tell me I know the frequency and I know the real value, tell me the imaginary value. You need to give the full array, okay? And in theory you have to give from 0 to infinity. In practice you will get data from low value to high value of frequency. Now, here omega is the variable here, x is the dummy variable. If you do the integration with the lower and upper limit, x will not come out of this equation. You will get this integration, you have an analytical expression, you may try doing this, numerically you can evaluate this. So, to calculate z real at one frequency, I have to know the z real at infinite frequency, I need to know this value. In addition, I need to know all the imaginary values, or skip this part now. To calculate the imaginary value at a frequency, any frequency, I need to know the real value of z at all frequencies and the real value of z at that particular frequency. Basically, I need to know all this data, and x is the dummy variable here, which basically is the frequency here. If I do the integration, I will get all the imaginary values. So, I will have to take this value, substitute omega equal to 2 pi f, here also omega equal to 2 pi f, and f equal to 1 e minus 3, f equal to 2 e minus 3, and so on. Each time I have to do integration. So, if I want for 1000 points, I need to do 1000 times this integration. If I do that, I will get set of values for z imaginary. Now, we are not going to lose data, hopefully not. We get data with frequency, real and imaginary. What we do is to get the set of values, predicted values, we call transformed values. So, I will use all the imaginary data and get the real values, I will use all the real data and get the imaginary value, and then compare with the data that is available. If they match, then I can claim most likely this data set has come from a system which does not violate linear, causal and stable criteria. Most likely, because this Kramers-Kronig transform is not a necessary and sufficient condition. In mathematics, you will say if and only if. So, in the Kramers-Kronig transform, if the system is linear, causal and stable, it will definitely satisfy this. But if the relationship is satisfied, I hope this is true, but it may or may not be true. It can come from a system which is not linear. In other words, if it does not satisfy Kramers-Kronig transform, I know there is a problem. If it satisfies KKT, most likely there is no problem, but I can't guarantee it. So, the best we can do is to check whether it satisfies this relationship or not. If it does not satisfy, we recognize there is a problem. If it satisfies, we hope everything is okay. But this self consistency check is available only when you have the real and imaginary part or the phase and magnitude as a function of frequency. Now, how do I implement it? How do I actually go about it? Because I do not have data from 0 to infinity, and I can nicely show many frequencies here, but in real life it will take very long time to get lot of data. Now, this is Ross McDonald, University of North Carolina, I think. So, if you do not really analyze the data properly, what is the point of taking the data? And as a corollary, Baukamp, if you do not have a validated data, what is the point of analyzing it? So, in impedance there is a possibility for us to validate it. So, first thing you should do when you acquire data is to subject it to KKT. When it is clean, then you analyze the data subsequently. So, Baukamp is in University of Twente, I think Netherlands, and he is given a program which you can use to verify whether data is compatible, KKT compatible. So, here I take an example circuit. This is consisting of passive elements, meaning it does not have any triode or diode or transistor, it has simple resistor and capacitor. A spectrum that comes from this will definitely be compliant, KKT compliant. That means it is coming from a linear, causal, stable system. There is no noise introduced here. I am simulating the data, and if I simulate the data in the complex plane plot, it will look like a semicircle starting at 20 ohms, ending at 120 ohms. We have seen this before. Now, if I do the transform and plot it in the Bode format, so I plot magnitude and phase as a function of frequency. The original data is shown as points here, and the transform data is shown as line here, and as expected they are matching. So, I want to show you, if there is a software, you can contact the faculty and get this from Professor McDonald in University of Berkeley. Double click the software, you will get something like this. This is the interface. Your data, without any header, you can have the data showing frequency, real and imaginary. Okay. In addition, you can also calculate. This CAL is the calculated value. Since I have already done this, it fills with this. Otherwise, you will have only frequency, real and imaginary. The EX stands for experimental data, and these two will be zeros. The way it is implemented, after loading the data, you have to say interpolate, and you can say calculate real, which means calculate the real value from the imaginary values. And do you want to integrate only within the limits? Integrate from 0 to infinity is what is required. but we have data from millihertz to maybe multiple kilohertz. So, I can do two things. One, I can say integrate only within this and hope everything is okay, or use some extrapolation. Whenever you extrapolate, there is a possibility that it will not work correctly, but extrapolation at the high, extrapolating the tails at the high and low frequencies is a possibility. We do not need to do this, it is the simulated data with good coverage of the frequencies. So, we will say yes. So, this plots the values. The segment here, basically what it does is, you want to do integration, it is a numerical integration. You can do numerical integration, and in real life you will have data points with some noise. So, you can say divide this into multiple segments, within each segment fit it to a quadratic equation or fit it to a straight line, fit it to a cubic equation, and then integrate that function. That is going to be better than trying to integrate through the numerical method with the points. Of course, if the points are very finely spaced, then you can use trapezoidal integration, Simpson rule, and get good data. If the points have noise, fitting it to a function locally, piecewise fitting it to a function and then integrating those is a better choice. So, in this case I am going to say 20 intervals with the polynomial order. If it is 1, it means it is a straight line segment. If it is 2, it is going to be a quadratic equation. And this works for fixed segment, it does not work for variable segment. In practice, ideally, if I have many data points in some frequency range and fewer data points in some frequency range, maybe I got data, they are noisy, I threw them away, remaining data I want to analyze. Then I might want to use different segment lengths, but it does not work here for whatever reason. So, you stick to fixed segment size, and instead of saying perform KKT, the command here is interpolate. The blue line is the line it is fitting, and that is what it is going to use for integration, which looks fair enough. You say okay, at this time it will be populated with all this data. This is the transform data, and I can also look at that saying I can plot experimental versus calculated. It's no good. I had taken a data which does not actually satisfy KKT. I have not taken the semicircle here, I have taken a slightly different. I can also say, now I can save this. If I save it, it is going to slightly alter the format, but it will save it in 5 columns. You can copy it and paste it into, for example, Excel, and you will get 4 columns with non-zero values, 5th column will be 0. I can say I want to calculate the imaginary and go through the same process, fixed segment size 20, 2, interpolate and claim OK. Now, you see the first, second, third columns remain as they are, 4th column has become 0, the previously calculated values have gone, 5th column is populated now. You should save this in a different file and then use Excel or some other software to get all the columns. That is how it is implemented. It is a free software, so we better take whatever is available. Okay. But you should use KKT to verify, and this is one free software, free meaning I had requested by email. I think if you request for academic purpose, you would get it for free and you can use it. So, using this software, I had generated these plots. In this example, I have simulated data, therefore, I have got good data from very low to very high frequency. So, let us pretend that we did experiment and due to some reason below certain frequency I could not take data, it is very noisy, or I had to finish the experiment and this is all I got. Now, I want to use this KKT and verify. So, instead of saying 0 to infinite hertz, I am saying 1 millihertz to 100 kilohertz. Now, I will say I have data only from 10 hertz to 100 kilohertz. That is not going to transform correctly. Even if I use extrapolation, sometimes it will work, sometimes it will not work. And this is not transforming correctly, not because the system is having any problem, not because system is not linear or causal or stable, because I am approximating 0 to infinity with a much lower or shorter truncated value, and that is not a good approximation. So, if you transform the data and it does not match, first thing you need to ask is, am I giving it in a wide enough range? Am I approximating the integral correctly? If I am approximating the integral correctly and then it does not match, I have a problem. If I am not approximating the integral correctly, I need to find some other way of handling this. That is one aspect. It is possible to use extrapolation. In some cases it will work and tell you it is compliant, some cases it will still say it is not compliant and you do not know whether it is problem with extrapolation or problem with the data. This is actually a photograph of Professor McDonald, who has been doing this for like many years, or you can say few decades. So, he has taken a data, iron dissolving sulfuric acid, and while taking the data they have superimposed a potential ramp, meaning the DC potential is supposed to be here and they are supposed to apply a AC potential here. Deliberately they have applied a potential, I do not remember whether it is going up or down, but the sinusoidal is superimposed along with the ramp. That means at the end of this, when you stop this data acquisition, potential is not here, it is at some other value and it has been changing throughout this experiment. So, artificially he has changed this to create a response from a system that is not stable. And if you take this data and do the transformation, you will find there is a clear variation. And if you take the data without the ramp, stable system, you will see that it matches well. I have not shown you the data here, but if you take a data for the same system without this potential ramp, it will match well. With the potential ramp, it does not match well. So, you get a data like this, you do KK transform, you will know there is a problem. It will not tell you the problem is in stability. It will tell you there is a problem, do not analyze the data thinking it is coming from a linear causal stable system. We have done some simulations where initially the potential is at some location. Okay. After some time it is gone up quickly and then stabilized here, or gone down quickly and stabilized here. That also is likely to happen in real life. Open circuit potential may drift over time and stabilize, and we have modeled this using an exponential function. Normally we will expect a semicircle if there is no stability issue. Because there is a stability issue, the stable one will give you a semicircle, the unstable one will give you a semicircle with a tail. Okay. Also notice that these scales are equal, they have to be equal, only then you can clearly see. Otherwise, if I truncate this or push this, it may even appear like this, which is caused by diffusion. We will come to that later, but this is just to illustrate that you have to look at the scales and you have to draw the scales correctly. And if I do transformation, original here is the data that I simulated, this is the transform data, and you can tell there is a problem. This is just again to illustrate that you should use KKT, and of course in these examples we are simulating the data, so we can take at any frequency. We can say take, meaning we can simulate that at any frequency. We can say go to very low frequency, very high frequency without any problem. Okay, we will continue tomorrow. Basically we can do this and show that in many cases you will find or you will capture the problem in the beginning, and whenever you analyze impedance data, first thing you need to show is I have performed KKT or equivalent test, it is satisfactory, and therefore analyzing the data. Okay. We will stop here today.